The universe is actively stretching its own fabric of space and time. This single idea of an expanding cosmos was so revolutionary it baffled even Albert Einstein, who later called his resistance to it his greatest blunder. You are about to learn the 20 specific discoveries that broke from classical physics and reshaped our cosmic reality. By the end, you will understand exactly how our universe defies prediction at nearly every turn. We will uncover why distant galaxies are racing away and what mysterious force is pushing them faster and faster. What part of our cosmic story do you find most difficult to accept? Edwin Hubble's discovery did more than just reveal a universe in motion. It was the first clue in a much larger cosmic mystery. That faint red glow from distant galaxies meant space itself was stretching, carrying those galaxies along with it like raisins in a rising loaf of bread. This single observation forced a monumental shift in thinking. If everything is moving apart, then rewinding the cosmic film reel implies a starting point, a moment of incredible density and temperature from which everything emerged. Yet this elegant idea of an expanding universe immediately raised a profound new question. A simple, constant expansion would see galaxies slowing down over time, their mutual gravity acting as a cosmic brake. For decades, this was the expected fate of the cosmos, a gradual and predictable slowdown. But the universe, as we would learn, had a far more dramatic and counterintuitive plan in store. What if the expansion wasn't slowing down at all? What if it was secretly speeding up? Two radio astronomers found themselves battling an inexplicable hiss. Arno Penzias and Robert Wilson were using a supremely sensitive horn antenna in 1964, intent on mapping radio waves from the cosmos. Yet no matter where they pointed their instrument, a persistent, uniform static remained. They meticulously checked every possible source of interference, even famously cleaning out a layer of white dielectric material, a residue left by pigeons nesting in the antenna. But the noise refused to vanish. This was not a technical flaw. It was a whisper from the dawn of time itself. They had accidentally discovered the cosmic microwave background radiation, the cooled remnant of the universe's fiery birth. This was the smoking gun evidence for the Big Bang, the faint afterglow of a moment when the entire cosmos was a seething, dense soup of particles and energy. This primordial light dates from a pivotal transition, about 380,000 years after the initial expansion, when the universe had cooled enough for atoms to form and light to travel freely for the first time. We see this event as a uniform globe bathing the entire sky, a snapshot of the infant universe. Its remarkable uniformity in all directions was a profound clue, but it was the tiny, almost imperceptible variations in its temperature that held the real secrets. These minute fluctuations, mere millionths of a degree, were the seeds of all future structure. They represented slight differences in density, the gravitational blueprints from which every galaxy, every cluster, and every vast cosmic void would eventually form. How could such tiny ripples dictate the fate of the entire cosmos? The answer lay in a force even Einstein could not have anticipated. This deep, uniform temperature across the cosmos presented a paradox that seemed to break the rules of physics. If you look at the cosmic microwave background in one direction and then turn to observe the complete opposite region of the sky, you are seeing light that has traveled for over 13 billion years from 2 points that should have never met. According to the standard Big Bang model, these two regions were simply too far apart for any information, any heat, to have traveled between them, even at the speed of light, across the entire age of the universe. They should be like 2 cups of coffee placed in separate, isolated rooms, each cooling at its own different rate. Yet when we measure them, they are precisely the same temperature to an astonishing degree. This is the Horizon Problem, a cosmic conundrum suggesting the universe, in its infancy, was somehow in perfect sync without any apparent means of communication. The solution required a radical rewrite of the universe's earliest moments. Physicists proposed a breathtaking event called cosmic inflation, a period of unimaginably rapid expansion that occurred in the first tiny fraction of a second after the beginning. Think of the observable universe starting as a subatomic speck, a single, homogeneous region where everything was in thermal contact. Then, in a flash far shorter than the blink of an eye, this speck underwent an exponential stretching, inflating to become larger than our entire visible cosmos today. This explains the uniform temperature because everything we see was once part of that same tiny, connected neighborhood. The mechanism behind this inflation involved space itself expanding faster than the speed of light. This seems to directly contradict Einstein's special relativity, which states that nothing can move through space faster than light. The crucial distinction is that inflation was not about objects traveling through space, but about the very fabric of spacetime stretching at a rate that carried regions apart from one another faster than light could bridge the new gap. It was a loophole in the laws of physics, allowing the universe to achieve a scale and uniformity that a simple, steady expansion could never explain. This inflationary idea did not just solve the Horizon Problem, it planted the seeds for everything to come, setting the stage for the next great cosmic surprise that would challenge our understanding of gravity itself. The universe's geometry holds a secret so precise it defies belief. Think of trying to balance a pencil perfectly upright on its tip, a feat requiring impossible steadiness. That same level of precision was seemingly required for the cosmos itself. For the universe to appear flat on the largest scales today, its initial curvature in the first moments had to be fine-tuned to an accuracy of 1 part in 10 to the power of 60. To grasp that number, it is like aiming for a target so exact that missing by the width of a single atom would mean complete failure. Without this perfect balance, the universe would have either collapsed back on itself almost immediately or flown apart into near nothingness long before galaxies could ever form. This was the Flatness Problem, a cosmic mystery suggesting our existence hinged on a starting condition of unbelievable, almost miraculous exactness. Yet cosmic inflation offered a powerful and elegant way out. That same period of hyper-expansion that solved the Horizon Problem also stretched the fabric of space so immensely that any original curvature, no matter how pronounced, was smoothed out to near-perfect flatness. It is like taking a tiny, wrinkled crinkle from a piece of paper and stretching it to the size of a continent. The surface would appear essentially flat to anyone standing on it. This meant the universe's large-scale geometry was not a lucky accident from a perfectly set dial, but a natural, physical outcome of its violent early growth. The Flatness Problem showed us that the fundamental properties we observe are not arbitrary but emerge from dynamic processes. This geometric solution, however, was just the beginning. How would our direct measurements of the universe's shape put our entire cosmic story to the test? The universe was keeping a colossal secret in plain sight. In the 1970s, astronomer Vera Rubin meticulously charted the speeds of stars orbiting within spiral galaxies. According to the established laws of gravity, stars farther from a galaxy's bright center should move more slowly, just as Pluto orbits our Sun at a more leisurely pace than Earth. Yet Rubin's data revealed something astonishing. Stars at the very outskirts of these galaxies were racing just as fast as those near the core. It was as if the entire galactic disk was embedded within a giant, invisible sphere of something, a hidden mass whose immense gravitational grip kept the outer stars from flying off into the void. This was the signature of dark matter. This mysterious substance does not glow like a star, absorb light like cosmic dust, or reflect it like a planet. It is completely invisible to every form of electromagnetic radiation we have ever devised, yet its gravitational influence is undeniable, a phantom force shaping the cosmos on the grandest scales. We now understand that this dark matter makes up roughly 27% of the universe's total content, meaning it outweighs all the visible matter in every star, planet, and galaxy by a factor of about 5 to 1. This single realization redefined the cosmic inventory. The universe we see is merely the glittering decoration on a framework built from something we cannot see. Further evidence for this hidden architecture mounted quickly: the way massive galaxy clusters warp the light from objects behind them, an effect called gravitational lensing, reveals the distribution of all mass, both seen and unseen. The precise patterns in the cosmic microwave background, the afterglow of the Big Bang, also bear the unmistakable imprint of dark matter's gravitational pull. These independent lines of inquiry all point to the same conclusion. Dark matter provided the essential gravitational scaffolding for the first galaxies to form, acting as a cosmic seed around which ordinary matter could gather and ignite. Its discovery forced a humbling admission: we have been studying the universe while blind to most of its material substance. If dark matter forms the invisible backbone of the cosmos, what other unseen force was waiting in the wings to take center stage? The cosmos had one more, even deeper secret to reveal. In 1998, two teams of astronomers were using distant supernova as cosmic mile markers, carefully measuring how the universe's expansion rate had changed over billions of years. Their expectation was simple and grounded in classical physics. The mutual gravitational pull of all the matter in the universe, the very dark matter we just explored, should have been acting as a cosmic brake, gradually slowing the expansion down over time. Yet the data told a completely different, almost unbelievable story. The most distant stellar explosions were fainter than their models predicted, meaning they were farther away than they should have been if the expansion had been steady or slowing. The universe's expansion was not decelerating at all. It was speeding up. Galaxies were flying apart from one another at an ever-increasing rate, as if some mysterious, repulsive force was actively pushing the fabric of space itself. This was the signature of dark energy, a mysterious component that makes up about 68% of the universe and counteracts gravity on the largest cosmic scales. This discovery represented perhaps the single greatest departure from Einstein's original vision. Decades earlier, he had introduced a fudge factor into his equations, a cosmological constant, whose sole purpose was to counteract gravity and keep the universe static, which was the prevailing belief at the time. When Hubble later proved the universe was expanding, Einstein discarded the idea as his greatest blunder. Yet here was the universe seemingly resurrecting his discarded constant in the most dramatic way possible. The observed acceleration suggests that empty space itself is not empty at all, but contains a latent energy that drives the universe's expansion. This concept fundamentally challenges our understanding of physics, forcing us to ask what empty space truly is. For this monumental finding, the leaders of the two research teams were awarded the Nobel Prize in Physics in 2011. Their work revealed a startling new cosmic fate. Instead of an eventual collapse or a gradual slowdown, the universe is destined for continued, endless acceleration, a future where galaxies will recede from one another until they vanish over the cosmic horizon. How would this mysterious force, this dark energy, continue to confound every attempt to explain its true nature in the decades that followed? The very fabric of the cosmos appears to be woven from uncertainty itself. Within the bizarre realm of quantum mechanics, a perfect vacuum is not truly empty. It seethes with a faint, energetic fizz, a subatomic dance where pairs of virtual particles and their antiparticles spontaneously blink into existence for the briefest of moments before annihilating each other. In our everyday world, these quantum fluctuations are fleeting and undetectable. But in the first sliver of a second after the Big Bang, during that explosive period of cosmic inflation, something extraordinary happened. As space expanded faster than light, these microscopic, random fluctuations did not simply vanish. Instead, they were caught in the stretching fabric of space-time and magnified from the quantum to the cosmic scale. Imagine a tiny, invisible ripple on the surface of a still pond suddenly being stretched into a continent-spanning wave. These amplified ripples in density became the primordial seeds for all structure in the universe. The faint temperature variations we observe in the cosmic microwave background, those millionths of a degree difference from one patch of sky to another, are the direct imprints of these quantum seeds. They are the fossilized blueprints of the universe's infancy. Where a region was ever so slightly denser, its gravity was a tiny bit stronger, pulling in more matter over billions of years. Where it was slightly less dense, it evolved into the vast, empty cosmic voids we see today. This incredible connection means that every galaxy, every star, and every planet originated from a random quantum jitter in the first instant of time. Satellites like Planck have mapped the pattern of these fluctuations with breathtaking precision, and the data aligns with the predictions of inflationary theory with near-perfect accuracy. This discovery fundamentally challenged the classical idea that the quantum world and the cosmic realm operated on separate, disconnected scales. It revealed that the largest structures we can observe, the great walls of galaxies and the sprawling empty voids, were born from the smallest possible physical processes. What profound secrets about the universe's first moments are still encoded in the detailed patterns of this ancient light? The infant universe was not silent. In its first few 100,000 years, the cosmos was a seething, opaque sea of particles and radiation, a plasma so dense that light could not travel freely. Within this hot primordial soup, gravity pulled matter inward, while the intense pressure of radiation pushed it outward. This cosmic tug-of-war generated powerful sound waves, spherical pressure fronts that rippled outward through the plasma at over half the speed of light. These were the Baryon acoustic oscillations, the literal sound of the universe's fiery youth. Then, at the 380,000-year mark, a pivotal event occurred. The universe cooled enough for atoms to form, suddenly becoming transparent and allowing light to stream across space for the very first time. This moment of liberation, which we observe as the cosmic microwave background, also froze the sound waves in their tracks. Each wave front left behind a spherical shell of matter, a faint, fossilized ripple in the cosmic distribution of galaxies. Billions of years later, this pattern remains subtly imprinted across the cosmos. When astronomers map the positions of millions of galaxies, they do not find a random scatter. Instead, they detect a slight but statistically significant preference for galaxies to be separated by a specific distance, a cosmic echo of that primordial ring. This characteristic scale, now stretched to nearly 500 million light-years across, serves as one of the most reliable standard rulers ever discovered. It is a fixed yardstick etched into the fabric of space itself. By measuring the apparent size of these acoustic peaks at different distances, and therefore different eras in cosmic history, astronomers can track how the scale of the universe has changed over billions of years. This technique provides a powerful and independent confirmation of the universe's accelerating expansion. The data reveals that the ancient sound waves appear more compressed than they should in a steadily expanding cosmos, indicating that space has stretched more than expected in the latter half of the universe's life. This finding aligns perfectly with the supernova evidence for dark energy, but it comes from a completely different method, one that does not rely on the intricate steps of the cosmic distance ladder. The detection of these acoustic oscillations is a triumph of modern cosmology, allowing us to use the fossilized vibrations of the Big Bang to measure the influence of the most mysterious force in the universe. How will this cosmic ruler continue to sharpen our view of dark energy's relentless push? Even our most successful cosmic stories contain a small, stubborn crack. In the universe's first few minutes, a brief and furious burst of nuclear fusion forged the earliest light elements. The theoretical predictions for how much hydrogen and helium should have been created align almost miraculously with what we observe throughout the cosmos. Yet one element refuses to fit the narrative. Lithium, the third lightest element, appears in ancient stars at only about 1/3 of its predicted abundance. This is the lithium problem, a quiet but persistent discrepancy that has puzzled cosmologists for decades. It is as if a single, crucial page was torn from the instruction manual of the universe's first moments. The models of Big Bang nucleosynthesis are so precise and so successful for the other elements that this lone anomaly stands out like a wrong note in a symphony. It suggests that our understanding of those initial nuclear reactions is subtly incomplete. Perhaps certain nuclear reaction rates need refinement, or maybe unknown particles influence the process, skewing the outcome for lithium alone. Another possibility is that these ancient stars, which we use as cosmic time capsules, have internal processes we do not fully understand, processes that slowly destroyed the primordial lithium over billions of years. This tiny mismatch reminds us that our picture of the cosmos is a living theory, not a finished text. It is the unresolved puzzles like the lithium problem that often guide us toward the next frontier of physics, hinting that even our most elegant models might be missing a crucial piece. What other elemental whispers from the dawn of time could reveal secrets we have not yet learned to hear? Our most trusted cosmic measuring sticks are telling us two different stories. For over a decade, a quiet but persistent crack has been growing in the foundation of modern cosmology, known as the Hubble Tension. At its heart is a simple number, the Hubble constant, which describes how fast the universe is expanding today. We have two primary ways to measure it. One method looks back to the dawn of time, using the detailed snapshot of the infant universe provided by the cosmic microwave background. The patterns in this ancient light, when run through our best models of cosmic evolution, point to a specific predicted expansion rate for the modern cosmos. The other method builds a cosmic distance ladder step by step, using nearby stars and brilliant supernovae in distant galaxies to measure the universe's current expansion directly. The problem is this: these two methods no longer agree. The local measurements consistently suggest the universe is expanding about 5 to 10% faster than the early universe data predicts. At first, scientists assumed this was a fluke, a systematic error that would vanish with more precise observations. But the opposite has happened. As our tools have become more advanced, from space telescopes to detailed sky surveys, the discrepancy has only hardened into a stubborn fact. This is not a case of blurred vision. It is as if two perfect clocks built by master craftsmen are ticking at undeniably different speeds. The growing consensus is that this tension is not a mistake in our measurements, but a clue. It may be the first sign that our standard model of cosmology, the very framework that has guided our understanding for decades, is incomplete. The universe seems to be whispering that something is missing from our equations. Could dark energy be evolving, growing stronger over time instead of remaining constant? Or perhaps dark matter and dark energy are not entirely separate, but interact in a way we have never detected. The most radical possibility is that Einstein's theory of gravity, the bedrock of modern physics, requires modification when applied to the vast expanse of the entire cosmos. This single discrepancy has ignited a global race to measure the Hubble constant in entirely new ways. Astronomers are now using the ripples in spacetime from colliding neutron stars, the predictable brightness of aging red giant stars, and the subtle distortions of gravitationally lensed quasars. Each independent technique acts as a new judge in this cosmic trial, weighing the evidence for a faster expanding universe against our established theories. The resolution of this tension holds the key to our next great leap in understanding. Will it force us to rewrite the laws of gravity or reveal a hidden chapter in the life story of dark energy? The answer is written in the receding light of every galaxy, waiting for us to finally read it correctly. The universe's expansion rate is not the only thing telling two different stories. A second, quieter discord has emerged from the shadows of cosmic structure itself, known as the S8 tension. While the Hubble constant measures the speed of the cosmic stretch, S8 describes the strength of the cosmic scaffold, quantifying how much matter has clumped together into galaxies and vast clusters over billions of years. Our most trusted prediction for this value comes from the pristine blueprint of the cosmic microwave background. The subtle patterns in that ancient light tell us precisely how much gravitational potential was seeded in the infant universe, forecasting a specific level of structure we should see today. Yet when astronomers directly survey the modern cosmos, meticulously mapping the distribution of millions of galaxies and measuring how their collective gravity warps the light from more distant objects, they find a slight but persistent discrepancy. The universe appears to be just a little bit smoother, with matter slightly less clumped than the primordial blueprint dictated. It is as if the cosmic construction project, while still magnificent, fell about 5% short of its original ambitious plan. This S8 tension is smaller than the Hubble conflict, but its implications are just as profound. It suggests a potential flaw in our understanding of how the cosmic web evolves. Perhaps dark matter, the invisible skeleton of the universe, is not entirely passive. Could these unknown particles interact with themselves or with other forces in a subtle way that slightly suppresses the growth of clusters? Or maybe dark energy, the force driving acceleration, began influencing the cosmos earlier than we think, gently pushing against the gravitational collapse that builds galaxies. Every proposed solution nudges our standard model in a new direction. If future observations from powerful new telescopes and sky surveys confirm that this smoother universe is real, it would force a fundamental rethink of the dark sector. We may have to accept that dark matter has a rich, complex physics of its own, or that dark energy's repulsive force has been subtly shaping the growth of structure for far longer than we ever imagined. This is the power of precision cosmology. It uses the universe itself as a laboratory, finding cracks not just in one measurement, but in multiple, independent pillars of our theory. What other hidden conversations between dark matter and dark energy are etched into the vast architecture of the cosmic web? Even our most pristine cosmic map, the cosmic microwave background, holds strange imperfections. Across the faint glow of the infant universe, scientists have discovered a series of large-scale anomalies that quietly defy a core principle of cosmology, the idea that the universe has no special place or direction. The most famous of these quirks has earned a dramatic name, the axis of evil. This is not a malevolent force, but a mysterious and unexpected alignment. The subtle hot and cold spots in the primordial light appear to be correlated along a particular line through space, as if the cosmos has a faint preferred axis. According to our standard models, such a coordinated direction should not exist. The universe should look statistically the same in every direction, a concept known as isotropy. Yet the data suggests a whisper of structure on the grandest possible scale. Other peculiarities add to the mystery. There is a vast, unexpectedly cold region in the southern sky, a giant cosmic void that seems improbably large. The two hemispheres of the sky also show a slight but persistent asymmetry, with one half appearing subtly different from the other in the distribution of its fluctuations. Furthermore, the universe appears to lack the large-scale correlations that our models predict, as if the cosmic tapestry is missing some of its longest threads. It is possible these are all just statistical flukes, rare random patterns that appear in any large dataset, or perhaps subtle effects from foreground dust within our own galaxy. But as our measurements grow ever more precise from satellites like Planck and future observatories, these anomalies have not vanished. They persist, hinting that our otherwise spectacularly successful model of the cosmos might be missing a crucial piece of physics. Could these patterns be an echo from a time before inflation, a relic of the universe's very first instant? Perhaps they point to exotic topological defects in the fabric of spacetime itself, cosmic strings or textures left over from primordial phase transitions. Some theorists even speculate that these large-scale alignments could be a bruise, the imprint of a long-ago collision with another universe in a vast multiverse. While these ideas remain highly speculative, the anomalies serve as a profound reminder that our understanding is still evolving. They are the faint, unanswered questions written in the oldest light we can see, challenging us to look deeper and wonder what other cosmic secrets are hidden in plain sight. These vast cosmic voids are far more than just empty space. They are the sprawling, silent deserts of the universe, regions so immense they can span hundreds of millions of light years and contain remarkably few galaxies. If our Milky Way resided in the heart of such a void, our night sky would be a near-perfect blackness, with the nearest major galaxy a faint, lonely smudge. Yet these voids are not completely barren. They hold a sparse population of isolated galaxies and are permeated by the tenuous threads of dark matter that still weave through them. Their existence creates a profound imbalance in the cosmic landscape. Just as air rushes to fill a vacuum, the immense gravitational pull from the densely packed walls and filaments of the cosmic web surrounding these voids creates a powerful suction effect. This generates a surprising cosmic current, a coherent river of galaxies flowing en masse. Our own local group, comprising the Milky Way and Andromeda, is caught in this stream, moving at a staggering 600 kilometers per second relative to the ancient light of the cosmic microwave background. This motion, known as the dark flow, is a ghostly tug from beyond the visible. The sheer scale and coherence of this movement is puzzling. It suggests the gravitational influence of structures so colossal they lie beyond our observable horizon, or perhaps points toward a subtle modification of gravity itself on the largest scales. By studying how galaxies move through and around these voids, astronomers can perform a unique cosmic autopsy. The subtle accelerations and flows reveal the distribution of all mass, especially the invisible dark matter that guides the motion. Each void acts as a natural laboratory, its sheer emptiness providing a clean backdrop against which the subtle pushes and pulls of gravity are amplified and made visible. What profound truths about the universe's hidden architecture are written in the silent, streaming motion of these great cosmic deserts? The cosmos has been caught in a lie of cosmic proportions. Our most powerful new eye on the universe, the James Webb Space Telescope, is peering back to the cosmic dawn, and it is seeing something that should not be there. Galaxies, not just faint infant smudges, but massive, brilliant, and fully formed cities of stars, shining when the universe was a mere infant of only a few 100 million years old. According to our best models of cosmic evolution, these behemoths simply did not have enough time to exist. The standard timeline dictates a gradual, hierarchical growth, where small protogalactic clouds slowly merge over billions of years to build the majestic spirals and ellipticals we see today. Yet here they are, impossibly early and impossibly mature, defying the simulations. This is the early galaxy problem, a direct challenge to the story we have told about the universe's formative years. How could such colossal structures assemble so quickly? The answers being debated are as profound as the discovery itself. Perhaps the very first stars formed with a ferocious efficiency we have never witnessed, converting nearly all available gas into stellar furnaces in one explosive burst. Maybe the initial recipe for star formation was different, birthing a generation of supermassive stars that lived fast and died young, seeding the cosmos with heavy elements far sooner than we thought possible. Another possibility strikes at the heart of the invisible universe itself. The properties of dark matter, the cosmic scaffolding, might need a revision. Could dark matter be slightly warmer or more interactive than our current cold, dark matter model assumes, allowing gravitational wells to form earlier and faster, giving galaxies a monumental head start? The most radical suggestion is that our cosmic clock is wrong, that the universe's timeline requires a subtle but significant adjustment. Each potential solution sends ripples through the entire foundation of cosmology. This discovery is a stunning reminder that our models are only as good as our observations. For decades, our theories were built on the light we could see, but Webb has pulled back a curtain, revealing a first act that is far more dramatic and complex than we ever imagined. As this telescope continues its mission, what other foundational truths about the universe's infancy will be rewritten by the light of these ancient, impossible galaxies? The energy of nothing might be the greatest scientific contradiction we have ever faced. We have seen how dark energy drives the cosmic acceleration, a force embodied in Einstein's cosmological constant, a simple number representing the energy density of the vacuum of space itself. Yet when we try to calculate this energy using our most successful theory of the small, quantum mechanics, we arrive at a result so catastrophically wrong it defies all reason. The theoretical prediction is a number followed by 120 zeros larger than the tiny value we actually observe. To grasp the scale of this error, it is the equivalent of a weather forecast predicting a hurricane would destroy a continent while outside, a single leaf trembles in the breeze. This is the cosmological constant problem, the most extreme mismatch between prediction and reality in the entire history of science. The vacuum, according to quantum theory, should be a raging sea of virtual particles boiling with unimaginable energy, an energy so potent it should have ripped the universe apart in its first instant. Clearly, that did not happen. So where did all that energy go? Why is the cosmos so incredibly, delicately calm? This is not a minor puzzle. It is a screaming indication that our understanding of how gravity works with the quantum world is fundamentally broken. The tiny value we observe seems to require a cancellation of almost impossible precision, as if two colossal, opposing forces in nature were balanced on a knife's edge. One proposed solution is as humbling as the problem itself. Perhaps our universe is just one bubble in a vast multiverse, an infinite froth of cosmic domains, each with its own random value for the vacuum energy. We simply find ourselves in one of the exceedingly rare bubbles where the value is small enough for galaxies to form and life to emerge. This is the anthropic principle, an idea that shifts the question from why the constant is so small to why we are here to observe it. Other physicists seek a more satisfying answer, proposing that a future theory of quantum gravity will naturally force the cosmological constant to zero, or that dark energy is not a constant at all, but a dynamic field that has slowly decayed over cosmic time. Resolving this staggering discrepancy is not just about fixing a number. It is the clearest path we have toward a deeper, unified theory of reality, one that can finally explain how the largest and smallest scales of the cosmos are woven together from the same fundamental threads. Every galaxy is caught in a dual dance of cosmic proportions. On one hand, they are passive passengers on the expanding fabric of space, receding from one another in what is known as the Hubble flow. This is the smooth, relentless stretch of the universe itself. Yet, each galaxy also possesses its own individual motion, a drifting pace known as its peculiar velocity. This secondary movement is a gravitational dance card, filled out by the immense, invisible pull of neighboring galaxy clusters, vast filaments of dark matter, and the deep gravitational wells of colossal superclusters. Think of it like leaves floating down a wide, steadily flowing river. The river's current is the Hubble flow carrying everything along, but the leaves also twist and turn, clustering together as local eddies and whirlpools tug them into smaller, more intimate motions. By painstakingly mapping these subtle drifts, astronomers can perform a remarkable feat of cosmic cartography. They can trace the gravitational tides back to their source, drawing a three-dimensional map of all the matter, seen and unseen, that is pulling on the galaxies around us. The results are startling. These are not just random, isolated movements. Researchers have detected coherent rivers of galaxies, vast streams all moving in the same direction across billions of light years. These bulk flows suggest a gravitational pull from structures of such immense scale they lie beyond the edge of our current observations, or they may hint that our understanding of gravity itself needs refinement on the largest cosmic stages. This creates a powerful, independent test for our models. By comparing the actual motions of galaxies, measured through their subtle red shifts and blue shifts, with the motions predicted from our maps of the galaxy distribution, we can check the cosmic ledger. Do the numbers add up? Does the visible and dark matter we believe is there create the gravitational pulls we actually observe? So far, the agreement is good, but not perfect. These subtle discrepancies are the new frontier. They are the faint tremors that might reveal whether dark matter behaves exactly as we think, or if the force of gravity subtly changes its character across the vast, empty voids between superclusters. What do these silent, streaming currents tell us about the true weight and arrangement of the universe's hidden architecture? Our cosmic census of the Milky Way's neighborhood has come up dramatically short. When astronomers run supercomputer simulations based on our standard model of cosmology, a universe dominated by cold, dark matter, they paint a bustling picture of our galactic surroundings. These virtual universes predict that a galaxy like ours should be attended by thousands of small, dark matter clumps, each massive enough to host its own orbiting satellite galaxy. Yet when we look up at the sky and count, we find only a few dozen of these faint companions. This glaring mismatch is the missing satellites problem, a quiet but profound challenge to our understanding of the universe's fundamental architecture. The simulations suggest a vibrant metropolitan area, but our telescopes reveal only a handful of isolated villages. So where is everyone? One compelling answer is that they are hiding in plain sight. Many of these predicted satellites may be so faint, composed of very few stars swimming in a massive sea of dark matter, that they have simply evaded detection. It is like trying to spot a single, dim light bulb from miles away on a foggy night. In recent years, this idea has gained support with the discovery of a new class of objects, ultra-faint dwarf galaxies. These are ghostly collections of stars, so diffuse that they were only found by meticulously sifting through data from the most powerful digital sky surveys. Their detection has partially filled the cosmic census, turning a glaring problem into a more subtle discrepancy, but a significant gap still remains between what we see and what the simplest simulations predict. If darkness alone cannot explain the full shortage, perhaps the story of star formation itself holds the key. Astrophysical processes within these small dark matter halos may have prevented most of them from ever lighting up. Intense radiation from the first massive stars or powerful winds from supernova explosions could have blown out nearly all the gas, the raw fuel for star formation, from these fragile gravitational wells. In this scenario, thousands of dark matter clumps still orbit our galaxy, but they are completely dark, invisible cities with no streetlights ever turned on. This explanation preserves the cold dark matter model but adds a layer of cosmic feedback we are still learning to quantify. The most radical solutions, however, suggest the problem lies not with the stars but with the dark matter itself. What if dark matter is not perfectly cold and collisionless? Alternative models propose warm dark matter, consisting of lighter, faster-moving particles. This would suppress the formation of the very smallest dark matter clumps, naturally leading to fewer satellite galaxies. Another idea is self-interacting dark matter, where these unknown particles can bounce off one another, smoothing out the cores of small halos and making it harder for stars to form. Each of these alternatives predicts a different number, distribution, and internal structure for the satellites we do find. This transforms the missing satellites problem from a mere counting exercise into a precision test for fundamental physics. The properties of the faintest galaxies we can detect act as a laboratory for probing the nature of the universe's dominant form of matter. The next generation of telescopes, like the Vera Rubin Observatory, is poised to resolve this discrepancy. With its unprecedented ability to scan the entire sky in exquisite detail, it is expected to discover hundreds, perhaps thousands, of these ultra-faint ghosts. A full census will tell us if we have finally found all the missing pieces of our local universe, or if the silence from the vast, dark halo of our galaxy is telling us something even deeper about the mysterious substance that shapes it all. The very hearts of galaxies hold a mystery that cuts to the core of dark matter itself. Our most detailed computer simulations paint a very specific picture of how this invisible substance should be arranged. They predict that dark matter halos should have intensely dense centers, with a concentration of particles rising sharply in a steep spike toward the very middle. Astronomers call this a Cusps profile, envisioning a mountain peak of pure dark matter at the galactic center. Yet when we observe the gentle rotation of small, faint dwarf galaxies, the story they tell is profoundly different. The way stars move within these galaxies suggests the dark matter at their hearts is not a sharp peak, but a flat plane, a core of nearly constant density. This is the cause versus cusps problem, a deep and puzzling contradiction between our theoretical expectations and the actual cosmic evidence. It is as if we predicted every city would have a single, towering skyscraper at its center, but upon arriving, we found instead a wide, level plaza. The simplest version of the cold dark matter model seems to get the large-scale structure of the universe spectacularly right, but it may be stumbling over the intricate details of individual galactic architecture. So what is smoothing out these dense central cusps? One compelling possibility brings the ordinary matter back into the spotlight. The violent lives and deaths of massive stars could be the sculptors. When these stars explode as supernova, they unleash titanic blasts of energy that can literally push the surrounding gas, and through complex gravitational interactions, this dramatic feedback may actually churn the very heart of the dark matter halo. Over billions of years, this constant stirring could gradually erase the sharp central cusp, transforming it into a smooth, flat core. Sophisticated new simulations that try to account for these fiery astrophysical processes are beginning to show this very effect, offering a potential solution that keeps our standard dark matter model intact. Yet another possibility is that the problem lies not with the stars, but with dark matter itself. Perhaps these unknown particles are not entirely invisible to each other. In a model known as self-interacting dark matter, the particles could collide and bounce off one another, much like molecules in a gas. These microscopic collisions would naturally transport heat and energy from the crowded outskirts into the dense center, effectively softening the sharp peak into a smooth, flat core. This would be a fundamental shift in our understanding, suggesting dark matter has a rich and complex physics of its own. The quest to resolve this puzzle is driving astronomers to peer ever deeper into the faintest hearts of galaxies. Each new observation of stellar motions provides a crucial data point, a clue to the true distribution of the invisible mass that holds these galaxies together. As our telescopes achieve higher resolution and our simulations grow more complex, we are closing in on an answer. Will the final verdict show that ordinary stellar explosions are sufficient to reshape the dark cosmos? Or will we be forced to accept that dark matter is stranger and more interactive than we ever dreamed? Our own cosmic neighborhood holds a secret in the motion of its largest galaxies. The Milky Way and its great spiral neighbor, Andromeda, are not simply drifting apart with the cosmic expansion. They are locked in a mutual gravitational embrace, falling toward one another in a slow dance that will culminate in a colossal collision billions of years from now. Yet the precise rhythm of this dance tells a story that does not quite match our expectations. For decades, astronomers have used a clever method known as the timing argument to weigh our local group of galaxies. The logic is elegant, like calculating the mass of the Sun by observing Earth's orbit. By analyzing the trajectories of the Milky Way and Andromeda, their approach speed and separation, we can work backwards to estimate the total gravitational mass that must be orchestrating their motion. The results from this local measurement are startlingly high, suggesting our local group contains significantly more mass than we can account for by simply adding up the visible stars and gas in all its galaxies. This discrepancy points directly toward the presence of immense, unseen dark matter enveloping our galactic home. But the plot thickens because the mass estimate from this orbital timing is often higher than values derived from other, independent methods. So what is causing this tension in our own backyard? Perhaps our local group is even more dominated by dark matter than we thought, with vast, diffuse halos extending far beyond what we can map. Or maybe the gravitational model itself is too simple, treating two majestic spirals as isolated points in space without accounting for the complex tug of smaller satellite galaxies or the subtle, constant pull of the expanding universe acting as a background force. The need for precision led to one of the Hubble Space Telescope's most delicate tasks, measuring the proper motion of Andromeda, the tiny sideways shift in its position against the backdrop of more distant galaxies. This was like trying to track the speed of a coin rolling on the other side of a football field. That crucial data stream allowed for far more sophisticated models, simulations that now include the entire local cosmic web, the gravitational influence of our nearest large galaxy cluster, and the intricate dynamics of expansion versus local collapse. This local laboratory forces us to ask profound questions. Is the timing argument revealing a hidden reservoir of dark matter right next door? Or could it be a subtle clue that our understanding of gravity itself requires a slight tweak when applied to the motions of galaxies over billions of years? The impending merger of our galaxy with Andromeda is not just a future spectacle. It is a present-day experiment, a slow-motion ballet whose steps encode the true nature of mass and gravity on the grandest of scales. A black hole's silence may be the loudest contradiction in physics. This final discovery brings us to the edge of known science, where the rules of the very large and the very small collide in spectacular fashion. The black hole information paradox begins with a simple, startling question. What happens to the information about an object when it falls into a black hole? According to the quantum laws that govern our reality, information can never be truly destroyed. It might be scrambled beyond recognition, but it must, in principle, be recoverable. Yet, when Stephen Hawking applied quantum theory to the curved space around a black hole, he found they should slowly evaporate, radiating away their mass until they vanish completely. This Hawking radiation, he argued, would be purely random, carrying no information about what fell in. If the black hole disappears, the information it swallowed seems to vanish forever, violating a foundational pillar of quantum mechanics. This paradox forces a stark choice. Either our understanding of quantum physics is wrong, or our theory of gravity is incomplete. Proposed solutions are as mind-bending as the problem itself. The holographic principle suggests that all the information about what falls into a black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, the surface that marks the point of no return. It is like a cosmic thumb drive storing a perfect copy of every atom that crosses its threshold. As the black hole evaporates, this information is slowly and meticulously released back into the universe through the subtle correlations within Hawking radiation. This idea connects to a profound correspondence that suggests our three-dimensional reality, with all its richness, might be a projection from a two-dimensional surface at its boundary, a concept that radically redefines the nature of space itself. Recent breakthroughs have added a stunning new layer to this puzzle, the concept of quantum islands. These are not physical places in space, but regions that emerge from the complex entanglement of quantum particles. According to this new framework, information that falls into a black hole does not simply sit on the surface. After a certain time, an island region appears just inside the event horizon, and this island becomes the new repository for the fallen information, allowing it to be accessed from the outside and eventually escape. This means the interior of a black hole is not a timeless prison, but a dynamic landscape where the very concept of inside and outside becomes blurred by quantum connections. The resolution of this paradox reaches far beyond the fate of a single star or galaxy. If information is truly preserved, even through the evaporation of a black hole, it suggests that the history of our entire cosmos might be encoded on its own cosmological horizon. In an accelerating universe, every galaxy will eventually vanish over our cosmic horizon, much like matter falling into a black hole. The principles we learn from black holes could therefore dictate the ultimate fate of all information in the cosmos. Will the story of every star, every planet, and every civilization be preserved forever on a universal hologram, or will it fade into a final, irreversible silence? Solving this quantum gravity puzzle may not just explain black holes, it could reveal that our expanding universe is, in the most fundamental sense, a story written in a code we are only just beginning to decipher. This journey through cosmic defiance reveals a universe that is fundamentally wild and unpredictable. The grand tapestry woven from Einstein's equations has been stretched, torn, and rewoven by observations he never could have anticipated. We now inhabit a cosmos where 95% of its content is completely invisible, where empty space pushes galaxies apart faster than gravity can pull them together, and where the faintest whispers from the quantum dawn dictate the architecture of everything we see. Each of these 20 discoveries, from Hubble's first glimpse of a receding cosmos to the stubborn tensions in our modern data, is not an endpoint. They are waypoints in an ongoing expedition, moments where human curiosity peeled back a layer of reality only to find a deeper, more compelling mystery waiting beneath. This is the beautiful, iterative rhythm of science. An answer is never just an answer. It is a key that unlocks a new room filled with even more profound questions. The accelerating universe, with its dark energy and dark matter, does not represent a failure of our understanding, but its ultimate promise. It challenges us to think bigger, to look deeper, and to accept that our most cherished theories are not sacred texts, but living guides that must evolve or be set aside. The next generation of observatories, from the Vera Rubin Observatory scanning the entire southern sky to the gravitational wave detectors listening to the ripples in space-time, are not being built to simply confirm what we already know. They are engines of surprise designed to probe these very tensions and anomalies. They will measure the Hubble constant with unprecedented precision, map the cosmic web in stunning detail, and perhaps even capture the ghostly signal of those first impossible galaxies. What they find may force us to rewrite the laws of physics once again, to finally grasp the nature of dark matter, or to understand why the vacuum of space has such a feeble energy. The greatest discovery waiting in the darkness is not a single fact, but a new framework, a theory that can seamlessly unite the quantum world with the cosmic stage. This story of 20 discoveries is ultimately a story about ourselves, about a species compelled to look up at the stars and not only ask where we came from, but to have the courage to follow the evidence wherever it leads, even when it defies our greatest genius. Which of these cosmic mysteries keeps you wondering about the nature of reality? Share your thoughts below and join us next time as we continue exploring the frontiers of knowledge.